Okay, today we're going to talk about the force of friction. Please have your Chapter 3 guided notes out. Be following along as we go through these slides. So, before I start talking about it, I want you to write down the definition for friction. Here it is. So, quickly jot that down in your guided notes. So friction is a contact force that acts in the opposite direction of motion. Now I've got a few pictures up here that I pulled this quickly off the internet that remind me of friction. Okay, I want you guys to look at this picture and tell me where friction is acting. This guy on the bike.
Tires in the road.
Okay, tires in the road. Yeah, there's friction between that tire in the road and between this tire in the road right there. Where else?
In the air.
Okay, yeah, the axles, these axles right here, here and there. Where else?
Air.
Okay, air resistance. Isn't that a form of friction?
Yeah.
Yeah, so air resistance. What else? Okay, the chain. Yeah, the chain's going to have friction on the sprockets on it, isn't it, guys? So this big sprocket here and the one in the back. Where else? There's more. Feet on the pedals. That's what's holding his feet on the pedals is friction. Okay. What about the hands? Yeah, hands got friction on it. Guys, friction is everywhere. It's kind of the point that I was trying to get with this picture. Friction is everywhere. Even think about a scuba diver in the water. Does he experience friction?
Yes.
Yeah, he's swimming forward with the flippers here. Friction is going to act in the opposite direction of motion. Okay, so if you look at a free body diagram, this is a free body diagram right here. If motion is going to the right, so your applied force is to the right, which way is friction going to act? To the left, and so that's why it's pointing to the left. Friction always opposes motion. Okay, so let's quickly talk about why friction occurs. Why do we have friction? Well, this is a pretty... This is a good slide. It really explains what causes friction. So friction occurs between the hills and valleys of one surface, and they're in contact with the hills and valleys of another surface. Now, even though it looks like an object's surface is really smooth, like this counter, it looks really smooth. But if you can look at it at the microscopic level, nothing is perfectly smooth. And you're going to have these little hills and valleys on one surface interacting with the hills and valleys of another surface. This one's even more zoomed in down here. And you can see these hills and valleys here. As you move across it, as this surface moves across the other surface, the hills and valleys of one surface kind of get, experience friction because they're being rubbed against the hills and valleys of another surface. So everything, if you looked at the microscopic level, would look like that. What's one way that we can reduce friction? What do we use to reduce friction?
Oil.
Oil. Okay? Some sort of lubrication, right? So if you think about oil, what does oil do to these valleys here? Well, it fills them up so that they're all filled and it's kind of a nice straight and level surface. Does it totally reduce friction? No, but it does help a lot, right? If your car engine with a piston and a cylinder, the movement's there. If you didn't have oil, would it last very long? No. And so, yeah, that's how we would reduce friction in that case. Okay, so we're going to learn how to calculate friction. The force of friction is calculated by multiplying the normal force. We talked about normal force before. So we multiply the normal force and this coefficient of friction for the surface. This equation is going to be the one that we're going to use the most today. And you're going to have to memorize it. We're going to use it so much for the rest of the year that you'll have it memorized. So how do you calculate force of friction? Well, you take this funny looking U symbol here and times it by N. What do those symbols mean? Yeah, this symbol is a Greek letter. It's called mu. and it represents the coefficient of friction for a surface. So this is mu. I'll always call it mu. And we times that by n. What's n represent? It's not newtons. The normal force. So we take this coefficient of friction, times it by the normal force, and we get the force of friction. Okay. Each surface has a different coefficient of friction. The more rough the surface, the higher the coefficient of friction. So let me ask you this to kind of emphasize that point. Which surface is going to have a higher coefficient of friction? Ice, like ice on a lake, or sandpaper? Sandpaper. It's got a rougher surface, so that means the coefficient of friction goes up. And if this number goes up, what happens to the force of friction, guys? It's going to go up as well. So the more rough the surface, the higher the coefficient of friction, the more friction you get. Okay. Well, there's two types of friction. The first one that we're going to talk about is kinetic friction. Kinetic friction. Before we start talking about it, I want you to write this in the margin where you see kinetic. Kinetic means moving. Okay, so when you're moving, kinetic friction is given this symbol mu sub k. K for kinetic. And it's the friction caused by a moving object. It's the friction caused by a moving object. So if I push this calculator across the counter, is there friction acting on it right now?
Yes.
Yes. And so what kind of friction would that be? Kinetic friction. Okay, let's contrast that to the other type, which is called static friction. In the margin by static, I want you to put not moving. That's what static means. It means it's at rest. It's not moving. Okay, it's given this symbol mu sub s for static. And it's the friction between the surface of an object that is not moving. So even though this calculator is sitting on the counter, is there still friction between the calculator and the surface of the counter? Yeah, it's still there. Okay, well here's the thing. Mu k, which is kinetic friction, is called the coefficient of kinetic friction and is usually smaller than mu s. So mu k is smaller than mu s. Let's talk about that with this slide. So, static and kinetic friction. I think we've all experienced this, but let's just read it. It says it requires more force to get an object moving than it does to keep it moving, because the coefficient of static friction is more than the coefficient of kinetic friction. I think we've all experienced this in our lives. If we're moving like a heavy object, like a fridge or something, some real heavy box across the floor, does it require more force to get it moving or to keep it moving? To get it moving, right? We've experienced that before. And so that's what this picture is showing us. This lady is trying to push this filing cabinet to the right. Okay, so this lady's trying to push the filing cabinet to the right. Guys, down here is a graph. Now this graph, the force is on the y-axis. Let's look at this. We've got to be able to understand this graph. Okay, she's pushing and nothing happens at this point. She's not putting enough force on it. Well, you get to this point and you finally reach this point where the cabinet starts to move right there. And that's because the coefficient of static friction is higher, so you've got to put more force. But once it starts to move, what happened to the force, guys? She doesn't have to use as much force anymore. And that's because the coefficient of kinetic friction is much lower. And so she can continue to move it even at a lower force. Anyway, I think we've experienced that before. It's harder to get an object moving than it is to keep it moving. And that's because the coefficient of static friction is a lot more, usually, than kinetic friction. Okay, this table, I want to go over it real fast. It's the different coefficients of frictions for different surfaces. If we go through it steel on steel, so just two pieces of steel, if you rub them across each other, It's got the coefficient of static friction and the coefficient of kinetic. Which one's greater? Oh, static. It takes more force to get them moving than it does to keep them moving. Some other interesting ones. What's the lowest coefficient of friction you see on there? Yeah, this very bottom one, synovial joints in humans. You guys taken anatomy, physiology yet? You talked about synovial joints or synovial fluid. So synovial joints, like the knee or the elbow, they have fluid so that the bones don't just sit there and rub against each other, and so you can decrease the coefficient of friction. Sometimes if you get your knee hit, it fills up with fluid. That's kind of the fluid that builds up there. But look here, the coefficient of static friction is quite a bit more than kinetic friction. So 0.01 and then compared to 0.003. So always, guys, this one is more than the kinetic one. Yeah, some other ones that are kind of interesting. Rubber on wet concrete or rubber on dry concrete. Which one has more friction?
Dry.
Yeah, the dry concrete has more friction. And is it safer to drive your car on a nice sunny dry day or a rainy day? Which one's safer?
Dry.
Dry, because you got more friction between your tires and the road, and your car's not going to slip out as easily. Okay. So anyway, every surface has a different coefficient of friction. Okay, so let's summarize friction, and then we'll do some practice problems. You need to know this equation. Force of friction is equal to mu times n, the normal force. There's two factors then that can increase the force of friction. Number one is the roughness of the surface. The roughness of the surface, which affects your coefficient of friction. If it's more rough, what happens to this coefficient of friction? It goes up. And what happens to your force of friction then? It goes up. So the more rough the surface, the more friction you will get. Okay, another factor that can increase the force of friction is weight. The weight of the object. Because the weight of the object affects what? Affects the normal force. Remember when we were drawing our free body diagrams, we had weight coming down, but most things are sitting right on the ground and it's not moving up and down. So what do we call this force that goes up? The normal force. And they're usually balanced. If it's sitting on the ground, they are balanced. So if you got a more heavy object, what's that going to do to the normal force? Well, it's going to increase it. If normal force goes up, what's going to happen to the force of friction? It goes up. Okay. So I usually like to demonstrate this with this demonstration, this garbage can right here. I'd like to prop this door open over here. I'd like to prop it open, and I'd like to throw that garbage can in there, but the garbage can just moves. The door is pushing the garbage can as it closes. So let me see if I can draw this so that people watching the video can get this. So I have a door. I put the garbage can in front of it to prop it open. The door wants to swing shut. There's two things that I could do to this garbage can to make it prop the door open and not slide shut. What are two things I could do? Increase the weight. I could put a heavier object in it, couldn't I? So I could put a lot of weight in there. If I put more weight, what's going to happen to the normal force? The normal force is going to go up, and if the normal force goes up, what happens to the force of friction? It goes up. Okay, so you could either put more weight in it, or I could do what? What's that? Yeah, I need to put something on the bottom of this garbage can to make its coefficient of friction go up or down? Up. If I put some rough surface on there, I don't know, maybe a piece of rubber on there, Would it make the coefficient of friction go up? Yes. And would that make my force of friction go up? Yeah. And that would hold the door open because there's more friction between the garbage can and the floor tiles. Does that make sense? So there's two ways you can affect the force of friction. The normal force or the coefficient of friction. Okay. I've got, I think, 4 practice problems, and then we're done. These are very important that you watch and pay attention and understand, because we're going to use it, like I said, for the rest of the year. Okay. So let's try number 8. Practice problem number 8. It says a hockey puck has a coefficient of kinetic friction of 0.1. If the puck feels a normal force of 5 newtons, what is the frictional force that acts on the puck? Okay, what's that equation for force of friction, guys? How do we find it?
Mu times N.
Mu times normal force.
Normal.
Can we just plug in and see what we get here?
Yeah.
Yeah. Plug and chug. Okay, so mu is 0.1. And we're going to times that by the normal force. What was the normal force?
5.
Normal force of 5 newtons, so 5 goes here. What's 0.1 times 5?
0.5.
Is equal to 0.5. Now it's a force. Friction is a force, so what units would I have? Newtons. Okay? Yeah. All forces have the same units. It's newtons. Very good. 0.5. Okay. Let's get to a little bit harder problem, more difficult problem. Number 9. Okay, it's got a lot of parts, A through F. So let's don't get overwhelmed by it. Let's just read the problem and do each part individually. Okay, it says, suppose a 10 Newton force is applied to the side of a 4 kilogram block that is sitting on the table. The block experiences a frictional force against the force that is applied. All right. A, draw a free body diagram for this block. I don't have a lot of space here, but in your notes, I would like you to draw the free body diagram. So that block is represented by a box in a free body diagram. Okay. I want to go back to the problem, and I want to underline everything that it gave us. Okay. 10 Newton force is applied, so that's our applied force. It looks like the mass of that block is 4 kilograms. There is a frictional force, and it acts against the force that is applied. Okay, so let's draw the free body diagram in A. It's sitting on a table. I don't need to draw the table, but what is pulling that block down onto the table? Gravity. So I'm going to put force of gravity. Could I also put weight, guys?
Yes.
Force of gravity is equal to weight. Okay, so they're the same thing. Now, it's not moving through the table. How come?
Because there's normal force.
Yeah, there's a normal force, which is equal to that force of gravity. So I'm going to put N going up. You guys remember this? Yeah.
Sure do.
It said that there was an applied force of 10 newtons. So I'm going to put that to the right. So force applied. And I'm going to put that it's 10 newtons. Told us it was 10 newtons in the problem. And then, what else? What's my last force? Friction. Which way does it point? Always opposes motion, so if you're pushing it to the right, it's going to go left. So force of friction. Did it tell us what the magnitude of that force was? No, it didn't. Now, one more thing before we're done with part A. Where it says the mass of the object is 4 kilograms, I want you guys to get in a habit of writing the mass inside the block. Okay, 4 kgs goes inside that block. Now, can we, that's our free body diagram. So we've got A. Check that one off. That's the free body diagram. Now let's go to B. What is the weight of the block? So I'm asking about the force of gravity, same thing. How do we figure that out? It's equal to what? mg, the mass times acceleration due to gravity. So the mass was 4, and what's g? 9.8? So grab a calculator, do 4 times 9.8. And the weight of it is equal to 39.2 newtons. 39.2. So we've got B. It's 39.2 newtons is the weight of that block. Now let's go to C. What is the normal force acting on this block? Good. Yeah, it's not moving up and down, it's at rest. So we know that the forces have to be balanced. That's according to Newton's first law, right? So that's 39.2. Newton's first law, object at rest will stay at rest unless it's acted upon by a net force. Well, in the up and down direction, it is at rest. There's no vertical motion. So these forces got to be balanced. Okay, so we've got part C. We've done that one. Part D. If the coefficient of kinetic friction is 0.2, what is the frictional force on the block? Okay, it goes back to what we just talked about. Frictional force is equal to mu times n. It told us what mu was, 0.2, 0.2. We're going to times that by the normal force, 39.2. Okay, so take 0.2 and times it by 39.2. 7.84, perfect, thank you. 7.84 what? It's a force, so it's newtons. So I'm going to put that on my free body diagram as well, 7.84 newtons. Okay, we've done D. Let's go to E. What is the net force on the block? Now I want you to look at the motion in the two dimensions, either up and down or left and right. Is there a net force up and down? We have 39.2 here, 39.2. No, it's balanced.
Oh.
So there's zero net force going up and down. But is there a net force going left and right? Yes. How do we find the net force? In physics, going to the right is what? Positive. So we're going to take 10. And in physics, going to the left is negative. So we're going to subtract 7.84. So our net force, I'm going to write it over here. Force net is equal to 10 minus 7.84. And that's equal to 2.16. Is that what you guys got?
Yeah.
2.16 what? Newtons. Okay. So we've got E. We've done part E. It has a net force of 2.16 newtons. Okay, now let's do part F and be done with this problem. It says, what is the acceleration of the block from the net force? So Newton's first law says, if you put a net force on it, what's it going to do? Well, it's going to accelerate. Newton's second law helps us figure out how much it's going to accelerate. What is the equation for Newton's second law? Dawson? What's the equation for Newton's second law?
F equals ma.
Perfect. F equals ma. I'm going to write that. F equals ma. And that F is a net force. Okay, now let's plug in and figure out what acceleration is. What is the net force? Well, we just found it was 2.16. So 2.16 is equal to, do we know the mass? 4. And we don't know acceleration, so I'm going to call it a. How do I solve for a, guys?
Division.
Good. Divide both sides by 4. So a comes out to be 2.16 divided by 4. 0.54. Thank you. 0.54 meters per second squared. Good. Wow, that's a good problem, isn't it?
Yeah.
That is crazy. Don't you feel like a real physicist now?
No. Not until we do a lab, will I
Feel like a real physicist. This is good stuff, guys. This is good stuff. We're using almost all of Newton's laws to get those answers, so good job. Okay. I got a couple more. Stay with me. I got a couple more. So let's do practice problem number 10. Okay. Practice problem number 10 says a horizontal force of 400 newtons is required to pull a 1,760 newton trunk across the floor at constant speed. Okay, it looks easy because it's only, what is that, one sentence long. But there's a lot of information in that one sentence. So, let's just break it down. Let's do part A first. It says, draw the free body diagram for this situation. Okay. It's a trunk, but I'm going to draw a box. Okay. They're sliding it across the floor. What force is pulling that trunk down? Gravity. I'm going to put weight this time. Does it mean the same thing?
Sure does.
Yep. Okay. It's not falling through the floor. It's at rest in the vertical motion. So what force is going up and counteracting that force?
Norm.
It's the normal force. What can we say about these magnitudes of the normal and weight?
Same.
They're the same.
No.
Very good.
Thanks.
Okay, and it said we had a horizontal force of 400 newtons. What do we call that force?
Force applied.
Good. That's force applied. And it's equal to 400. So I want you to put that 400 newtons by force applied. Okay. Now, if you're pushing it to the right, is there a force going to the left?
Yeah.
Yeah, what's it called?
Friction.
Force of friction. It didn't tell us what it equaled. We might be able to figure that out here in a second. Okay, but then there's this one thing here. It says it's a 1,760 newton trunk. What does that mean? That's the weight.
Yes, that.
That's the weight. Good. So 1760 comes down here. It's equal to 1760 newtons. So does that also tell us the normal force?
1760.
Yep. The normal force is equal to 1760. They're balanced. Man, this is good stuff, isn't it, guys?
This is awesome.
This is awesome. I love physics.
I love it too. It's actually not a constant speed, so there's no net force.
Perfect. Perfect. Yeah. Cole's got it. So he says they're pulling this trunk across the floor at constant speed. If they're at constant speed, is there a net force?
No.
No. So if there's 400 newtons to the right, there's got to be 400 newtons to the left. So we know the force of friction is 400 newtons. Okay, so there's our free body diagram. We've got it. Okay, put a check on A. We've done that part. Okay. Now let's do B. Find the coefficient of kinetic friction.
Okay.
Is there an equation that has the coefficient of friction in it? Yeah, force of friction is equal to what? Mu times normal force. Do I have the force of friction, guys?
Yes.
What is it? 400. So we're going to put 400 in for that. I don't know what the coefficient of friction is yet. We're going to solve for it. Do I have N, the normal force?
Yes. Yeah.
1760. Okay. Now, how do you find mu? Divide by 1760 both sides. Over here it cancels out. So mu is equal to 400 divided by 1760. 0.23, yes. So mu is equal to 0.23. Now, mu is an interesting number, a value. It doesn't have units. So you don't have to worry about putting units for the coefficient of friction. How awesome is that problem?
Awesome.
Yeah, that's pretty cool.
No problem.
Okay, now we've done part B. Was there a C?
No.
No. Okay. Okay, I wanted to go back to this. Guys, this is a huge piece of information. Constant speed means what? Balanced forces, or the net force is zero. Good job. Okay, practice problem 11. This is my last one. We can get through this, and we'll be done for the day. Okay?
Awesome.
Awesome. This is good. I love physics.
I do too.
Okay. Okay, let's try it. Okay, stay with me, guys.
Yes.
Okay. An object weighing 40 newtons rests on a surface. The coefficient of friction between the surface and the object is 0.35. A. What is the frictional force between the object and the surface? I'm going to hit pause on the video. I want you guys to try this on your own. If you're watching the video, hit pause. Try and see if you can answer A and B on your own without help. Okay? And then once you have an answer, hit play and see if you got it right. Okay, so let's see if your answer is right, if you got an answer. And if you didn't get an answer, let's see where you got stuck and see if we can fix it. Okay? So what I would always do with the physics problem is draw what, Cuban?
A diagram?
Picture.
The full body diagram.
Oh.
The full body.
Not happening.
It's a free body diagram. Free body. Yeah. But it's a full body diagram. Okay, Cuban, they're called free body diagrams, so let's draw it. I don't really have a lot of space, so I'm going to draw it down here. Okay? Always draw it as a box. Okay? Now, let's read it. It says it weighs 40 newtons. What is that? Which way does that go?
Gravity.
Yeah, it's force of gravity. So weight is equal to 40 newtons. Okay, so I'm going to write that. And it rests on a surface. So what can you say about the force that's counteracting that?
It's 40 newtons.
Also 40 newtons. What's it called, though?
Norm.
The normal force. Thank you, Trevor. Okay, I hope we can see that. If it's not falling through the floor, so these forces here and here have got to be balanced. Okay. The coefficient of friction between the surface and the object is 0.35. I want you to get in the habit of somewhere down by your free body diagram putting mu is equal to 0.35. So let's just make note of that. We might need it. In fact, we're going to use it later. Okay. A. It says, what is the frictional force between the object and the surface? How do we find force of friction? It's equal to what? Mu times normal force.
Yeah.
Okay. So do I have enough information to find the frictional force? Yeah, I've got mu, so 0.35. And we're going to times it by the normal force, which is 40. So 0.35 times 40, what's that?
14.
14.
14. Hey, I got that.
14 what? 14 newtons. Yeah, it's a force. So let's draw that. I always put friction to the left for some reason. So force of friction is equal to 14. 14 newtons. Okay. So A is done. Let's go to B. It says a 20 Newton force is applied to pull the object horizontally. Let's draw that in our free body diagram. Force applied. And it's equal to 20 newtons. What is the magnitude of the unbalanced force? Okay, now is there an unbalanced force up and down? No. 40 and 40 cancel each other out. That's 0. But is there a net force or an unbalanced force left and right?
Yeah.
Yes. And in physics, when you go to the right, it's what? Positive. If you go to the left, it's negative. So to figure out the net force here, you take everything positive, which was 20, and you subtract everything that's negative, which was going to the left, which was 14. What's 20 minus 14, guys?
6.
6 newtons is your net force. Okay? That's the magnitude of the unbalanced force. So force net is equal to 6 newtons. That's part of our answer. But it also said, what is the acceleration of the box? Now, here's a huge hint. Whenever it's talking about forces and it's asking you about acceleration, which one of Newton's laws should we use?
That second one.
Second law. What does that say, Hayden?
F net equals m times a.
Good. Most famous equation in physics. F equals ma. Now let's plug in all the information that we have. Do we have the net force?
Yeah.
6. Do we have the mass?
40.
We don't have the mass, do we? Do we have A? Nope. That's what it's asking us. We don't have A. Okay, so now what do we do? How many of you guys got stuck right here? Okay. If you got stuck right here, how do we figure out the mass of this object?
40 divided by.
Here's a hint. Do we have the weight of the object? And weight is equal to what, guys? mg. So if the weight is 40, let's plug in 40 for the weight. We don't have the mass. Do we have g?
Yes.
What is it on Earth? 9.8. Okay, how do I get m by itself? Divide by 9.8. Okay, over here. So 40 divided by 9.8 will give us its mass. 40 divided by 9.8. Okay, mass is equal to 4.0. Quit making fun of me. 4.08 what? 4.08 what? kgs. Good. Mass is always measured in kilograms. So now we can plug that in for m down here. So 6 is equal to 4.08 times a. Now, how do I solve for the acceleration?
Divide.
Divide by 4.08.
1.47.
Okay. So good. 4.08 divided by... No. 6 divided by 4.08.
Yeah.
What did you get, Cole?
1.47 meters per second.
1.47. That's exactly right. 1.47. And what's the units?
Meters per second squared.
Meters per second squared. Okay. Hey, we can do this. Before I end the video, I want to review a couple of things. Some equations that we've learned up to this point. How do you find force of gravity? Force of gravity is the same thing as weight. How do you find it?
M times G.
Mass times gravity. Okay. Newton's second law. What is it?
Force equals mass.
Force equals ma. Then we're adding a new equation today. Force of friction. How do you find it? Mu times normal force. Okay, those 3 equations. You've got to know them. Okay. We can do this stuff. All right. You now know enough to do the friction worksheet in the student workbook. So friction worksheet. Head to that place in your student workbook and get that done, and hopefully this helped.